Okay, so here's one more example. And so far we've seen one that is a value returning function. We've done a void function. This is a value returning function, but it has more than one parameter. So I mean, you can use void functions, value returning functions. You can have different numbers of parameters. It just depends upon the recursive function that you're writing. So in this example, we're going to take a value n and raise it to a positive power p. This only works for a positive power. So, it'll work for like 2 to the third power or 3 to the fourth power. So the base case or the stopping case is going to be when the power is 0, then it returns a 1 because anything to the 0 power is 1. The general case, it's going to be the number times the number raised to the p minus 1 power. So it's just whatever the number is, and then that same number, but this time it's raised to a smaller power. So you can see here, this can easily be done as a for loop, but we're going to look at a recursive solution to this problem. Okay. So if the power is equal, so two parameters, n is the number, p is the power. If the power is 0, return 1, else return n times, and then you're going to call the recursive power function. Now remember, it's got two parameters, n and the power minus 1. So here's an example. If our function call is 2 raised to the third power is, well, this is just a cout statement. And this would, let me fix this. This would be, right, we're going to call our recursive power function with 2 and 3. That means we're going to raise 2 to the third power. 2 to the third power is 8, so that's what we should hopefully get. All right, so when we start, we're passing in 2, right? Your 2 from here, and your power 3 into here. So if the power is equal to 0, no, it's not, we return 2, and then we call the recursive power function again, still with our number n, which is 2, but this time the power is less 1. Now remember, that's what the recursive function looks like. All right, so right here we have our recursive call. Now remember, you still have the 2 times here. That's still happening, but hasn't finished. So now we call this, and we pass 2 and 2. If the power is equal to 0, no, it's not. It's equal to 2, so we're going to return the value of n, which is 2. And, you can't put 2 and 2 in here. I'm just, this is n and pow, but I'm just trying to show what it is at this point. 2 times, and then we call it same value of n, 2, but 1 less power. So 2 times recursive power, and we pass it 2 and 1. Right? So now we come out to here. And again, this is n and power. I'm just showing them as 2 and 1 so you can keep track of this. The power is 0, no it's not, it's 1, so we return 2 times, and again recursive power, still 2, but this time the power is 0. So this will come out here, right? And now this is the base case, the power is 0, so this function returns 1, right back to here, because that was that recursive call. And now this function can finish, return 2 times 1, right? So this is going to return 2, right back to here. And this function is going to return 2 times 2, right, which is 4, right back to here. And this is going to return 2 times 4, which is 8, right back to here, which is the original recursive call. And that's what we would expect to happen. Okay. Now I'm going to scroll down here and just talk a little bit about, now that we've seen 3 examples, we're going to talk about Stack Overflow. So part of your memory is reserved to support function calls. So each function call places a new stack frame on the stack. And that stack frame, which could be a structure maybe, will hold local parameters, local variables, and things like the address where it needs to return to when the function is completed. And upon return, like it'll pop it off the stack and then it'll be deleted. So with iterative algorithms, this is not a problem. The depth of the refunction calls is small, usually 3 or 4 maybe, but recursive calls, it can be a problem since the function calls are the primary iterative control structure. In this example, we see another example of tail recursion, and I talked about in an earlier video, when the recursive call is the last thing, like you see there, it's probably better to write that with a different type of loop and not use recursion. Whereas in our right vertical example, this was not the case. This is a good example of what to do with recursion. So the problems you have are the potential for enormous space demands, the time required to build these activation records or these frames, place it on the stack, pop it off the stack, and delete it from memory. But the benefit would be some data structures and algorithms are recursive by nature. Things like trees, heaps, and sorts, and recursion leads to a very compact and elegant solution. So keep in mind 2 big things. If you have a recursive function, it should not ever contain a loop. You're using recursion instead of the loop. That's probably the most common mistake that I see students make. You have to have a base case that will end the recursion. If you don't have a base case, you will have an infinite loop. So you have to be careful of that as well. So in that general case, something has to happen that gets you closer to the base case. All right. So for example, up here, this is the thing that gets me closer to a base case of the power being 0.